Hello, welcome to our unit, or excuse me, our topic, and our video on measurement error and uncertainty. This is not a topic that really gets tested all that much on the Regents, but it's an important topic if you want to be science literate, and everyone should want to be science literate, whether you're planning on studying more science in college or beyond, wherever you go after high school, or you just want to be an informed citizen. First thing I'm going to ask is for you to measure this box. Now you should have a protractor, hopefully. My protractor looks like this. Not only does it have inch markings, which we will not use, it's also got centimeter markings along the inside and then the angle markings along the top. I want you to measure how long this box is in centimeters. So I'm going to line this up, put the 0 right on the edge of the box, and I'm going to measure all the way out to the other edge. And to me, let's see here, that looks like it's about, not quite, let me adjust this a little bit. Okay. Not quite, a little bit more than 6.8, and maybe you guys are getting a different perspective, but from my perspective, not quite 6, a little bit over 6.8, but definitely not quite 6.9. So how long is this box in centimeters? Well, I might write down as something like this, 6.83 centimeters. Now, if you were doing this, you might have just written down, okay, 6.8 or 6.9 or 7 centimeters, okay? It turns out that any of those answers actually wouldn't be that, I would not accept those answers. However, I would definitely accept, instead of 6.8, I would accept 6.80 or 6.90. I might even accept 7.00 depending on the mood I'm in, okay? The reason I'm saying that it makes a difference whether you say 6.8 or 6.80, it has to deal with, are you doing as good a job of measuring as you should be? Are you being as accurate as possible, but are you doing the process correctly? Measurement's actually kind of trickier than you think. You really need to know the accuracy of the tool that you're using. So this is a protractor. It's got centimeter markings. It's actually, if you look, it's got even smaller markings. There's 10 lines between the centimeters. Those are millimeter lines. Those are millimeter markings. This is the same as on your standard meter stick. Okay? A meter stick also has millimeter markings. Those are the smallest markings on there. So the smallest markings indicate millimeters. Remember, the prefix milli means 10 to the negative third. Another way of thinking about it is there's 1,000 millimeters in 1 centimeter, or in 1 meter. 1,000 millimeters in a meter. When you're measuring, you always want to record data to one place past the smallest markings. So that means when we're using a meter stick, we should measure objects to the nearest tenth of a millimeter. Let me say that again. The millimeter lines are these smallest lines right here. So when we measured that box, we said it was somewhere between 6.8 and 6.9 centimeters. The 0.8 and 0.9 represented the millimeter place. In order to be as accurate and as thorough as possible when measuring, we want to go one place past that. So our rule for measurement is to always record data to one place past the smallest markings. So that means that 6.83, the 0.8 was, this is the millimeter place, we want to record to one place past that, this would be fine. Just 6.8, you're not being thorough enough, okay? We know that it's somewhere, if we're looking at 6.8, there's a literal line for 6.8. If you're saying 6.8, then that means that you didn't even look to see if it was exactly on 6.8 or not. We can make that one place farther estimation. 6.84 would have been fine, 6.82, 6.81. You could have even said 6.80, and what that's implying is you looked one place past that smallest marking, and you said, nope, it ends right here. It's exactly on it. 6.8, you didn't look for that check that last place beyond the smallest markings. So that's our rule for when we record data. The rest of this is going to be about different types of error in a topic called uncertainty. Because even though I measured this to be 6.83 centimeters, is that exactly perfect? Is that the exact answer? Like, I mean, there obviously does have to be one true answer, but can we ever really get to that? Can our measurement ever figure out what the exact length of something is, or the exact mass, or the exact time. No, it can't. No measurement is ever going to be exactly perfect for a number of reasons. The first being measuring tools are always imperfect, okay? This is a really good protractor, but it's not perfect, okay? No measuring tool will ever be perfect. The idea that no measuring tool is ever perfect is called measurement uncertainty. Measurement uncertainty falls into this category of things that we call errors. If you're a baseball player and you make an error, that means you made a mistake, okay? It means that a ground ball was hit to you and you missed it, or you dropped a pop fly. Those are errors. Those are bad. Errors in science are not necessarily bad. Some of them are actually unavoidable. You will always have them. It doesn't mean you've done anything wrong. It's just something that you have to keep in mind. Error in science really refers to things that prevent you from making the perfect measurement. And again, it's never possible to make a perfect measurement. It's never, ever going to be possible to tell exactly how big or how heavy or how long something is. So what we do is we provide our best measurement of it. It says best guess here. It's not really a guess, but our best efforts towards measuring it. But in addition to that, in addition to saying, this is what I think the measurement is, we're also going to give a range. That range is known as the uncertainty that the true measurement is likely within. I'll demonstrate this in a picture in just a second, but let's go back up to our box for a second. For this box, we would write our answer with uncertainty like this: 6.83 plus or minus 0.01 centimeters. This part right here, the plus or minus 0.01 centimeters, that's the uncertainty. What that does is it says my measurement was 6.83 centimeters. However, based on the tool that I was given and my use of the tool, I'm fairly confident that even though this probably isn't perfect, the quote-unquote true measurement or the true value is somewhere within 1/100th, that's 1/100th of a centimeter from that. So the true measurement is somewhere between 6.82 and 6.84 centimeters. That's called an uncertainty, and you're going to see that increasingly as you move up through science. If you take science in college, you'll definitely run into uncertainties. There's rules for coming up with uncertainties. It's not just always 0.01. That just happened to be the answer this time. For non-digital instruments that you actually have to read, that don't just provide you an answer, that don't just pop the answer on a screen. For non-digital instruments, the uncertainty is 1/10 of the smallest gradation, which just means marking, on the instrument. So that's actually kind of similar in this case. The smallest markings on here are millimeters, so our uncertainty is 1/10 of a millimeter. If we remember, if we're measuring in centimeters, the place to the right of the decimal point is the millimeter place. So our uncertainty is 1/10 of a millimeter, which would be 0.01 centimeters. It's a little confusing, but you'll get the hang of it the more you do this. For digital instruments, such as a stopwatch. Oh wow, I've never done that before. That's pretty cool. For a stopwatch, the uncertainty is half of the last digit place. So that means that since I stopped this exactly at 1 second, half of the last digit place, this is really 1.00 seconds. Half of the last digit place means 0.5 of this second decimal. So that means the last digit place is 0.01. Half of that is 0.005. So that means that even though the stopwatch says 1.00 seconds, the true value of that time interval really could have been anywhere from 0.995, in which case we'll just round up to 1 second, seconds, to 1.005, okay? So anything below that would just round down to 1 second. That's how uncertainty works for digital instruments. Okay, so what you can really think of, if you want a picture of uncertainty, here's your, I don't want to call it best guess, but this is your best effort, I know I'm writing really small, measurement right here, your uncertainty is kind of like a bracket around that. So in other words, you're saying, here's what I think the answer is, here's what my measurements came out to, but this, and I know I'm not probably exactly right, but I'm fairly confident the actual quote-unquote true value, which you can never actually measure, is somewhere within this range. Okay, that's how an uncertainty works. And in labs, we're going to practice calculating uncertainties. But measurement uncertainty, this idea that measuring tools are always imperfect. By the way, uncertainties are associated with measuring tools. So for instance, this has a certain uncertainty, the stopwatch has a certain uncertainty, the meter stick has a certain uncertainty. Every measuring tool has a specific uncertainty that you can use, that you would write down. Measurement uncertainty, the idea that measuring tools are always imperfect, isn't the only type of error. There's at least one other type of error which is totally unavoidable. We're going to talk about that now. In class, if we were in class, I would have everyone get a meter stick now, and we would measure the length of a floor tile with uncertainty and record it here. So with the meter stick, the smallest lines are millimeters, so you're going to go to the next place out for your measurement and for your uncertainty. So a typical measurement might look something like this. So someone might get 30.50 for the measurement, and then they're going to add on the uncertainty. So now you're not really adding, but you're going to write it in addition to, so that your measurement with uncertainty is 30.50 plus or minus 0.01 centimeters. So that means that you measured, your best effort measurement is 30.50 centimeters, but based on the tools you used and your competency with them, you're fairly confident that the true answer, quote unquote, true value, is somewhere within a 1/100th of a centimeter. So anywhere from 30.49 centimeters to 30.51. However, if we were to do this in class, not everyone is going to get exactly that. Some people are going to get 30.55 centimeters. Some people will get 30.60 centimeters. Some people get 30.40 centimeters. All the tiles in my room are the exact same size. So what's going on here? Not everyone's getting the same answer. Does that mean that someone is wrong and some other people are more right? No, not necessarily. Anytime you have multiple measurements being made, even if it's the same person measuring the same thing, you're not going to always get the exact same answer. You're going to encounter what is called random error. And I really don't have room for a definition here, so we're going to kind of write it over here. Random error is natural, and we put this in quotes, spreading of data around a quote-unquote true value. And remember, it doesn't necessarily mean someone is more right and someone is more wrong, because it is impossible to get an exact true value. It's impossible. You're never going to do it. Not that it doesn't mean you're a bad scientist, it's physically impossible to get an exact value for something. So random error is just this idea that even if so in this example, we were all measuring the same thing, but we were all making different measurements. Just because some people had one answer and some people had another does not necessarily mean that one is right and one is wrong. Random error is the idea that even if the same person measures the same thing the same way, they'll never get the exact same answer. There's going to be a spreading of data due to little factors that you cannot control. Okay, things that are physically not within your control. You didn't do anything wrong. It's an unavoidable consequence of measurement. It will always be there. So imagine that we only made two measurements. Someone measured a floor tile as 30.50. Someone measured a floor tile as 30.40. How do we know which one's closer? How do we get more confident in which one is the better measurement? Well, maybe we have another person measure. Maybe this time they get 30.47. And then we have another person measure and they get 30.49. The more data you get, the more confident you can be in an exact answer, and the more you can see which data might be an outlier. So in order to reduce random error, I shouldn't say to reduce because you can never completely eliminate it. In order to reduce the effects of random error, it is highly suggested that multiple trials are done. In other words, you want to take the same data point at least a couple different times so that you can see, okay, I'm fairly confident in this, okay? The more trials you do, maybe not the same data point, I shouldn't say that, but the more trials you do, the more confident you can be in your answer. So measurement uncertainty and random error, you can minimize them. You can never completely eliminate them because no measuring tool is perfect and you're always going to have some random spreading of the data, random error. There are, however, two types of errors that are more avoidable. One that's really avoidable that you should never have, and another that you will run into, and our main job in a lab is to minimize it. The first one, the really bad type of error, is called human error. You never ever want to say that there is human error in your experiment. This is any sort of error that is basically you didn't use common sense, you didn't pay attention, you didn't follow the procedure closely, okay? You are never allowed to say that something went wrong because of human error, because that's basically just admitting I didn't do what I was supposed to. If you think that there's human error, if you think that you did something that wrong, go back and fix it. Some common types of human error. Math errors. Everyone makes math mistakes. I make math mistakes all the time. However, in a final write-up or a final question answering section of a lab, if you're saying, I think my lab results weren't that accurate because I made math errors, well, then go back and fix the math errors. That's not a good reason for why you didn't get something right or why you didn't get an accurate answer. Using equipment wrong. If you're using equipment in a manner that is inconsistent with what you are supposed to be doing, or you're reading it wrong, or you're using it for some purpose that it wasn't intended for, that is a human error. That's unacceptable. Here's one I see all the time. People say, and this is a human error, if we're doing a lab that involves some timing, people will say, well, my results are wrong or might not be accurate because I wasn't accurate with my stopwatch. Humans are very rarely accurate with stopwatches, okay? And we just got done saying no measurement is ever perfect. So are you ever going to be perfectly accurate with a stopwatch? No. But that's already been taken into account. That's why we have measurement uncertainty. If you say I wasn't accurate with my stopwatch, I'm picturing you either deliberately didn't take the right time, or you weren't paying attention and clicked your stopwatch way too early, like outside of common sense too early or outside of common sense too late. That's not a good reason for error, okay? There are errors with a stopwatch that are a little bit more reasonable, but just saying I wasn't accurate is not at all acceptable. You need to be more detailed than that, or you need to use your stopwatch better. Just so you know, on a lab, when you are asked for ways to reduce, let me move this up a little bit. When asked for ways to reduce uncertainty or correct error on a lab, saying human error contributed to inaccuracy is never acceptable. Never, ever. All right. Let me just make sure that we got that, all that. Okay. And let's flip over to the back. Okay. So I mentioned there was one other type of error, and wasn't as bad as human error, and it's actually similar to human error, but there is a difference, and it's a little tough to tell the difference sometimes. It's called systematic error. This is error. It's still, we want to minimize systematic error, and it is possible to have low or very close to zero systematic error, but it's not quite as bad as human error. Systematic error is you did everything right, but maybe you didn't know that you had a faulty piece of measuring equipment, or maybe there was something in your procedure that you just didn't consider, okay? It's more of a science error than a I just wasn't paying attention error. That's what systematic errors are. So systematic errors can arise from either flawed assumptions or procedures, or faulty measuring equipment. Basically, we're not saying you shouldn't realize it. But a systematic error is something you kind of have to think about. It's something that isn't like glaringly obvious that went wrong. Whereas like human error, like a math error or using equipment wrong, that's glaringly obvious that you did something wrong. So some examples of systematic error. Let's say that you had a meter stick. And this, by the way, does not happen very often. And if you wanted to claim this as a systematic error, I would ask you to prove it. Let's say your meter stick at the meter stick factory was actually printed, the lines and spacing was printed wrong. It was printed on a yardstick. If you measured using that meter stick, which is really a yardstick, you would be overcounting the number of meters in a certain distance. And that would shift your answer off. By the way, systematic error, it shifts all of your data. Okay, that's the definition of a systematic error. It always shifts your data to be too high or too low. Again, if you wanted to claim this one, I would ask you to prove that your meter stick isn't a meter, which is much too hard for anyone to do and too time consuming, but it is an example of a systematic error. Another common systematic error is anticipating something happening. Imagine a stopwatch. You're timing the time it takes for something to happen, such as an object to fall. Let's say that you start your stopwatch, and then as the object is falling, you realize that you started a little late, so you think to yourself, I'm going to stop it exactly when it hits the ground. What you're probably going to do is stop it a little bit too early. So think about it like this. If you start your stopwatch late, start it late and stop it early, you measured a time period that's much shorter than you should have, okay? Because you're starting it late, probably because it takes a little time for the information to get to your brain to tell your brain that the object is falling, and for you to click on the stopwatch. That takes time. Then if you stop it early, you're measuring a time that's much too short. Instead of anticipating, okay, what you need to do is you need to somehow remove that anticipation. So one common technique is if you're timing something, actually don't look at it. Wait for the person who's dropping the object to say start, and then listen for the object to hit the ground, and then you can stop it. That way, you start late, but you also end late, and you'll get a much more accurate time. And then another common one, which you've probably encountered before, is not zeroing out a scale. These are all more or less like equipment malfunction, or I guess this one is a procedural thing. Most of the time when we talk about systematic error, it's something in your procedure that you didn't account for, like air resistance, or I didn't realize that there was friction on something, or I didn't take this other factor into account. Those are very experiment dependent though. Not zeroing out a scale would be like if the scale had nothing on it but was reading like 0.1 kilograms and then you put an object on it, the scale is going to include that extra 0.1 kilograms in your mass. That's a systematic error. Your mass has been shifted to be heavier than it actually is. So those are the 4 types of error. Measurement uncertainty, no measuring tool is perfect. Random error, natural spreading of data around the quote-unquote true value. Human error, you did something very obviously wrong and you shouldn't have. And then systematic error is really what we're trying to reduce the most and eliminate in an experiment. Assumptions that you made that aren't valid, or you have measuring equipment that's not working, or that is a little bit faulty. 2 more topics. Percent error. You learned this in chemistry. Every once in a while in labs, you're going to be asked to find the percent error to compare your answer to an established, and I'm going to put again in quotes, correct value. There's no way for us to ever know what the exact correct value of something is, but we have established values that are really, really, really accurate. So we treat those, especially at this low level, as quote unquote correct. The equation is not in the reference tables. It was in the chemistry reference tables. It's not in ours. We're still going to use it a couple times, so I'm writing it here. You can always go back here and look for it. Percent error is your measured value minus the accepted value, the established correct value, divided by the accepted value, multiplied by 100. A little note here, it does not matter if your percent error is negative. If it's negative, that's fine. Include the negative, but it doesn't mean anything that important to us, okay? It doesn't really matter all that much. An example, when conducting an experiment to measure the acceleration due to gravity on Earth, your final answer is 9.43 meters per second squared. If the accepted value for acceleration due to gravity on Earth is 9.81 meters per second squared, what is the percent error in your measurement? By the way, you're going to see this number over and over again in this class. The first thing we're going to do when solving a math problem in physics is we're going to write out the equation. Percent error equals, I'm just going to abbreviate here, most of the time you won't have to, measured value minus accepted value over accepted value times 100. You can't just throw the numbers in automatically. You have to write out the full equation first with no measurements in there so far, okay? Once you do that, now you can bring in your measurements. But you do have to bring in your measurements with their units. So the acceleration is 9.43 meters per second squared. That's the measured value. That's what you measured. By the way, the seconds squared, that's just a unit. Doesn't mean you have to square anything. Minus the accepted value of 9.81 meters per second squared over 9.81 meters per second squared. I did that last time too. 9.81 meters per second squared times 100. Okay? Measured value minus accepted value over accepted value times 100. We get a percent error calculation of percent error equals negative 3.87%. Negative 3.87%. That's a pretty good percent error. Really good is within 5%. Anything under 10% is generally considered, yeah, you did a good job. Anything about 20% and over, you really should go back and try that experiment again and see if there was any systematic errors that you could fix or correct. Check your assumptions, make sure you're doing everything correctly. Our last topic for measurement error and uncertainty is just a little bit on accuracy and precision. These two words are different. They have different definitions, but they get used interchangeably by people. They are different. Accuracy refers to how close a data point is to the quote-unquote accepted value. If a data point is really close to the accepted value, what that means is that there's low systematic error. The data hasn't been shifted away from the quote-unquote true value that much. If you have precise data, that is how close data points are to each other. If your data points are all grouped very close together, then that means that you have low amounts of random error. Remember, random error makes your data spread out. If your data is all close together, just for whatever reason, you have low random error. Some experiments, there's naturally lower random error. Some experiments, the random error is naturally a little bit higher. So how close a data point is to accepted value and how close data points are to each other, those are two different things. To illustrate these differences, we have these targets with little X's on them. Imagine that you were shooting at a target and you were trying to hit the bullseye, the center. The first one, these data points are all very close to the center of the target and they're very close to each other. This is data that is both accurate and precise. This is what you want, obviously. You want accurate and precise data. The second target is data that is not very close to the center of the target, so it's not accurate, but it is precise. It's precise because all the data is close together. So the random error was really good, okay? There was a low amount of random error, but you had somewhat of a systematic error, which shifted all your data up and to the right. Maybe there was a little bit of wind and you weren't taking account for that if you're like shooting at a target. The third target shows data that's all relatively close to the center, to the bullseye. So I would say this is accurate on kind of a relative scale. But the data is not close to each other. It's not precise, meaning there's relatively high random error. So maybe more trials, more shots at the target would reduce this, and you would have, in general, a closer spread among the extra data. And then finally, this last target, you can see that the data is not really all that close to the center, so it's not accurate. And the data is also not close to each other, so it's not precise. You have high levels of both systematic and random error in this example. That does it for this set of notes on measurement error and uncertainty. It's really kind of a grab bag. I'm showing you a lot of different stuff just to show you that there are some different things to consider when we're doing labs. You need to be aware of the different types of error. You need to be aware of how to measure correctly, and you need to be able to make a percent error calculation to find systematic errors in your work, to avoid human errors, and to be able to say whether your data, upon looking at it, okay, is it accurate? Is there low systematic error? Is it precise? Have I taken enough data points so that the random error is relatively low? That's it for measurement, error, and uncertainty. And actually, I think it's all for all of the information you need for your first quiz, which will be upcoming. If you have any questions, as always, don't hesitate to reach me in class, in school, or electronically. Talk to you later.